This results in a power law, but the resulting graph differs from the web graph in other ways, such as the presence of small, densely connected groups. Models and more broad network features have been presented and investigated. Pancho et al., for example, provided a variant of the rich become a richer generative model that considers two attachment rules, a preferred attachment mechanism, and a uniform choice solely for the most recent nodes. See Dorothy and Means book for a review. Some mechanisms, such as superlinear preferential attachment and second neighbor attachment, produce networks that are scale-free in the short term but diverge from a power law as they grow larger. Penn et al. Proposed a somewhat different generative model for web links. They looked at communities with a specific interest in a topic, such as a university homepage, public firms, media, or scientists, and discarded the main web hubs. The distribution of linkages in this situation was no longer a power law, but rather resembled a normal distribution. The authors suggested a generative model based on these findings, which combines preferred attachment with a baseline likelihood of obtaining a link. Another generative model examined by Marcus et al. Is the copy model, in which new nodes pick an existing node at random and copy a fraction of its links. A power law is also generated as a result of this. The addition of new nodes to the network does not have to be a criterion for constructing a scale-free network. Caldwell et al. Suggest treating the structure as static and drawing a link between vertices based on a specific attribute of the two vertices involved. Once the statistical distribution for these vertex qualities is defined, it turns out that static networks can acquire scale-free properties in some cases. Scale-free generalized model. The modeling of scale-free complex networks has seen a surge in interest. Several adaptations and generalizations and the revamping of past mathematical works have followed Barabasi and Albert's recipe. A model is a scale-free network if it has a power law distribution, and a model of that network is also a scale-free model. Features. Many real-world networks are scale-free, necessitating the use of scale-free models to describe them. Price's plan calls for two ingredients to develop a scale-free model. Adding or deleting nodes is the first step. Typically, we focus on expanding the network by adding nodes. Preferential attachment, the probability that fresh nodes will be attached to the old node. Some models can also work statically, with the number of nodes remaining constant. It's also worth noting that the fact that preferential attachment models produce scale-free networks doesn't mean that this is the process behind the evolution of real-world scale-free networks. Alternative mechanisms may be at work in real-world systems that produce scaling. Examples. Several attempts have been made to generate scale-free network properties. Some instances are as follows. The Barabbas-Albert model is a model developed by Barabbas and Albert. Kanchenjunga constructs a 2L model by taking into account the relevance of each of a target, node's neighbors, and preference attachment. In the 2L model, a node's attractiveness is determined not just by the number of nodes linked to it, but also by the number of linkages in each of these nodes. The creation of transient scale-free networks is demonstrated by a variation of the 2L model, the K2 model, in which first and second neighbor nodes contribute equally to a target node's attractiveness. As long as the network is small, the degree distribution appears to be scale-free in the K2 model. But as the network grows larger, major departures from the scale-free regime arise. As a result, the relative attractiveness of nodes varies over time, a phenomenon that is also evident in real networks. Model of mediation-driven attachment. In the mediation-driven attachment paradigm, a new node with m_mm edges chooses one existing linked node at random, and then connects with m_mm of its neighbors, who are likewise chosen at random. Ki is the inverse of the harmonic mean of degrees of a node I_is ki neighbors.